In this series of videos, we've been talking about single joint control, and specifically about how we do position control given that DC motors control velocity as a result of changing the voltage. We already looked at open loop control, and today we're going to be looking at feedback control. In these videos, we're going to get an introduction to what feedback control is, and then we'll be focusing on one particular kind of feedback control, which is on-off. Feedback control, as opposed to open loop control, is a type of control that requires a sensor that will feed back information about the joint position to the controller. Feedback control typically requires both hardware components and software components. The hardware components include both a motor and a sensor. But simply having these components are not sufficient to accomplish feedback control. We also have to have some software components. We have to have a software component in which we read the value of the sensor. Then we have to use that sensor value to calculate the error in the position. The error in the position is the difference between the position that we want the joint to be at and the position that the joint actually is at, which we determine by reading the sensor. Next, we have to use that error which we've calculated to calculate a motor voltage or speed based on the error. Finally, we send that speed command to the motor. The last thing that we do in this process is we loop back up to read the sensor again, and we repeat this process in a repeating loop. This repeating loop is what constitutes the software component of closed loop control, also known as feedback control. We can draw these hardware and software components into a diagram called a block diagram. In drawing my block diagram, I'm going to start out by drawing my motor. The motor receives an input, and that input is voltage. The output of the motor is velocity. Now, I'm next going to show the output of the motor being read by the sensor, but I have to add a little additional component here because the sensor does not read the motor velocity. The sensor directly reads the motor position. So in my diagram, in my block diagram, I'm going to add a block that says that it is an integrator. There's no specific hardware or software component that needs to be incorporated for this integrator. It's simply a physical conversion that this velocity does in fact get converted to position, which is what we read with the sensor. So I can now draw in the sensor. I've shrunk my diagram up a bit here because I need some space to show what happens to the sensor signal when it comes back. The sensor reads the actual position of the motor. And we're going to compare that actual position to the desired position, the position where we want the motor to be. Here I've shown an input of the desired position, and I'm going to put a little summing junction here that shows that we're going to take the desired position and we're going to subtract from that the actual position, and that will produce our error. This arrow here is error. Now, the last thing that we need is another block right here that converts our error into the voltage that we're going to send into the motor. This block right here is what we call our controller. The controller is the software component that converts our error into voltage. If we look back up at the software components that we listed, the components of feedback control, here's that piece right here. Calculate a motor voltage based upon error. This is our controller. And our controller, move this back onto the screen here. The controller is an equation. Notice that I put the controller under a software component. The controller is an equation which we write into the control program, which takes in error and produces out a motor voltage, or in our case with digital pins, a pulse width modulation duty cycle. Let's take a look for a moment at what this feedback control loop, what this block diagram looks like physically. Here I'm showing a picture of a motor like you might see for sale when you're shopping around for motors for your robot applications. This motor comes already set up for you to do feedback control with it, at least with the hardware components. This part right here, this is the motor, and you see that it has a number of wires coming off of it. 2 of those wires would be for power and ground. But then you also have another part attached to the motor right back here. This part is a device that's called an encoder. We'll learn more about encoders in the sensors section of this class, but suffice it to say for now that an encoder is a device, a sensor, that reports the angular position of the motor. This encoder has a shaft that is attached directly to the motor shaft, and so the encoder is able to measure the rotational position of the motor as it's running. Here's a picture of the motorized slide potentiometers that we use in class. Here we have the motor terminals to which we can apply a voltage to set the speed of the motor. In the body of the slide potentiometer, along the whole length of the body, there is a resistive material inside of this device. It's a strip or a film of resistive material. If we would measure the resistance across this strip of resistive material, the resistance would be something like 10 kiloohms. Now, inside of this slider, there is a piece of a resistive, or a piece of a conductor, and this piece of conductor is called a wiper. The wiper is attached to the slider, but it also contacts the resistive material. If we would measure the resistance between the wiper and the end of this resistive material, the resistance would be variable. It might be equal to, in this picture, let's say 1 kiloohm. As the slider slides to a different position, the resistance between the wiper and this end of the resistive material would become larger. What we can do then is we can put a 5-volt signal into one end and connect the other end to ground, and then measure the voltage output at the wiper, and that signal will tell us the position of the slider. So let's look back for a moment at our block diagram. The motor, the integrator, and the sensor are typically all attached to the same hardware device. What we have to do to implement feedback control is we have to take the sensor output, send it into an input pin on our controller, use the controller to compare our desired position to the actual position and find the difference between them, and then use the error to calculate a voltage with an equation that we write in software. The equation that we write in software for this controller is what defines the difference between one kind of feedback control and another kind. In the next video, I'm going to talk about what kind of equation we write for on-off feedback control.